let's talk about this question here. So we're given this matrix A and vector B, and then we're also given that reduced echelon form of A with B augmented on it. Right, so we can kind of think about this as they took that matrix A, they augmented on the column B, and then went ahead and row reduced that. And at the end, we ended up with this row reduced matrix 102, 5, 0, 1, 3, 1, 0, 0, 0, 0. And then we're asked to answer several questions about when different matrix equations have solutions or don't have solutions, whether the columns span R3, if the columns can, or if a certain vector can be written as a linear combination. And all of those, we know that those relate back, or we can answer them if we consider these pivot positions in our echelon form or reduced echelon form of the matrix. So I'm going to go ahead and do is just circle those pivots, and we'll kind of write down some facts here. So I notice that there is a column without a pivot, and I also notice that there is a row without a pivot, and maybe I'll do that here in yellow. Just going to write that down. And those two pieces of information are going to allow us to answer a lot of these questions. So let's go ahead and read each of the individual options we're given, and then use this information we have and kind of see what piece gives us what thing. Okay, so the first one says that AX equals B has exactly one solution. So there's two different things I need to know. I need to know that it has one solution, and then it has only one solution. So in order to have a solution, and I'll write this at the bottom, in order to have a solution, I need to make sure that there's not a pivot in that augmented column. So we already have this matrix A with B augmented on that's all the way row reduced. There was not any pivots in that augmented column. So maybe I'll list that here as well. There was no pivots in that augmented column. So I know that there is a solution. But now I also need to make sure that there's exactly one solution. So we have exactly one solution when we don't have those free variables. So exactly one solution is no free variables. But because I have a column without a pivot, I know that there's a free variable, which tells me when I do have a solution, so if we have a solution, then we have infinitely many solutions. So in this case, I had no pivot in the augmented column, so there was a solution, but because I had a column without a pivot, I had that free variable, so I was going to have infinitely many solutions. So it is not the case that I have exactly one solution. Okay, moving on, AX equals 0 has a non-trivial solution. Again, to get a non-trivial solution, I know AX equals 0 always has a solution. So a non-trivial solution comes from that free variable. So again, because I have that column without a pivot, I am going to have a non-trivial solution. So that one is correct. The next thing that we have here is that the columns of A span R3. For this one, it's important to remember what that means, what it means for the columns of A to span R3. So I'm just going to go ahead and write that up here. It means that every vector in R3, they don't necessarily we're not going to think about them as columns. Every vector in R3 we'll start with saying, in the span of the columns of A, which is the same as saying is a linear combination of the columns of A, which is the same. Remember, think about those sets of linear combinations. I can think about having a solution to that AX equals basically anything that I put here. So no matter which B I augmented on, I'm always going to get a solution. Let's look at this the one below it as well. For all C in R3, AX equals C has a solution. That's exactly what I said right here. So in fact, that's really a definition that the columns of A span R3. So either these two are going to be true at the same time or they're going to be false at the same time. Okay, so what are we thinking about? We're asking ourselves if it's true that no matter what vector I put over here, I don't have to use the specific B, I'm allowed to put any vector I want over here. And then I'm going to row reduce, and I want to check what happens over here to see if there is a solution. Now what we notice is for this special B that I chose, we did get that nice 0 here in the augmented column. But if I had picked a different B, I could end up with some sort of non-zero element here. I could have gotten some non-zero for some other vector. And that way I would have had a whole bunch of zeros and then a non-zero element. So I would have gotten a pivot in that augmented column. The reason that would be a pivot is because it would be the first non-zero element in that row, because the rest of the elements in that row were already zeros. So if you have a row without a pivot, you could possibly get, so it's possible to get a pivot in the augmented column. In fact, there's always going to be at least some vector you can get that's going to give you a pivot, because you just pick some vector here that doesn't have a 0. So I'm going to pick maybe something like 1, 1, 1. And then I reverse those row reductions. So this is saying reverse row reduction, even though you can't really read it. I'm going to reverse those row reductions, and I can figure out what that vector C up here would be that would row reduce down to that 1, 1, 1. Okay, so if I have this row without a pivot, it's possible to get a pivot in that augmented, let me just finish writing this, column. So I can get AX equals B has no solution for specific B's. So maybe I'll call it a C so it's not confused with the B that I was already given for some vector C. And therefore I don't get that for every vector I have a solution, and that means that the columns of A do not span R3. So neither of those are going to be true. Okay, moving down, this one is just about this vector B again. The vector B can be written as a linear combination of the columns of A. That's exactly the same as saying that AX equals B. Remember the way that we defined this matrix vector multiplication is by taking those linear combinations. So does this have a solution? Well, again, that's just for this specific B. So we go back to our definition. In that specific B, we did get that nice 0 there, so there was a solution. So we can write B as a linear combination. And the last question is just about the system of equations. So again, the system of equations, if we look, those coefficients are 2, 1, 7, 1, 1, 5, and then 1, negative 1, negative 1. And the thing that it's equal to is that 11, 6, 4, so that's exactly B. So this is exactly the system of equations that corresponds with this augmented system AB. And we know that reduces down, and it has a column. There's no pivot in the augmented column. So for both of these, I know there's that no pivot in the augmented column. And because of that, this system is consistent. It does have a solution. So that's how we can use this information we have, this information about those locations of the pivots, to answer these questions. Hopefully this helps. If you have any questions, let me know.